Today in this session, we will solve one question, and that is related to the equilibrium. It's a ladder against a frictionless wall. So let's read the question. It says, a 3.2-meter ladder leans against a frictionless wall. James stands on the ladder at 0.6 meter along its length from the bottom. The ladder makes an angle of 25 degrees with the wall. James has a mass of 50 kilogram and the ladder has a uniform distributed mass of 12 kg. So the question is, first question, calculate the reaction force the wall applies to the ladder. And the second part is calculate the reaction force the floor applies to the ladder. So these are two questions. And I just drew this figure. If you look at here, the ladder, which is 3.2 meter long. It's making, so the wall is here. This is our wall. And the ladder is 3.2 meter. That's leaning on the wall. And at 0.6 meter from the bottom, James is standing, and it is Wj is the weight of James. And because the ladder is uniformly distributed, so it means it's WL, the weight of ladder, is actually at half of its length. So half of 3.2 is 1.6. So WL is weight of ladder. So we have to solve this question, and we would see how to do this. And we know how to do this. It's an equilibrium because the ladder is resting at the wall. Um, we know there are two types of equilibrium which we have to see. One is the translation equilibrium and one is the rotational equilibrium. So the equilibrium, translation equilibrium, the condition is sigma fx, all forces in x direction should be equal to 0, and sigma fy, so these are. And for the rotational equilibrium, we know sigma tau, that is that should be equal to 0. So the torque, sum of the torque clockwise and anti-clockwise should be 0. So we would be doing this question in this manner using these two equilibrium conditions. Okay, let's start solving this question. And here I have again drawn the diagram in green, and we have Wj, which is the weight of the James, and WL, which is the weight of the ladder. And we would do it by a rotational equilibrium. So first of all, let's look what is this angle, which is here. Because it's a right angle triangle, and we know it's a 25, so 90 minus 25, 90 minus 25, because the sum of should be 180 in the right angle triangle, and the other sum should be, the sum of the other two angles should be 90. So 5, and we have now here 865. So it means this angle here is actually 65 degrees. So now we would see the rotational equilibrium. We will see what is anti-clockwise and clockwise moment, and we would equate them. So, but before that, it's given that the wall is frictionless. The wall is frictionless, so it means it would give a reaction force which would be perpendicular. If it would not have been a frictionless, we would have another component. So presently, this is a frictionless wall. Therefore, we have a reaction which is 90 degrees to the wall. So I can put this as a F wall. So let's put uh, our rotational point, we say, where it has to at the tip of the ladder. Yeah. So we put at this point, maybe let's put it as a name. So we are putting it as a pivot on which this ladder is maybe rotate. So let's write what is a clockwise rotation, clockwise. So first of all, we would say clockwise moment. So if you see the moment due to Wj is clockwise, the moment due to WL is also clockwise. Why? No. So the moment due to Wj is anti-clockwise, due to WL it is anti-clockwise, and if you see the moment due to F wall is actually clockwise. So if you see, we would see, we would say F wall, which we have, times. Now we have to times it. And we know in the moment it's the perpendicular distance. So actually we are saying this distance, let's take it y. So we have to find what is the y. And it's easy to find. Why? Because we know the total length of the ladder which is given to us is 3.2. So this was 3.2 meter, which is given 3.2 meter. So I would just say if we have something like sine 65 degrees, so it is y upon 3.2 because perpendicular over hypotenuse. So y is equal to sine 65 times 3.2. So if you calculate sine 65 times 32, let me calculate it. Sine 65, which is 0.9 0.906 times 3.2 times 3.2. So this is becomes 2.9 Newton. 2.9 Newton. So it means not sorry, it's not Newton, it's meters because we are this is 2.9 meter. So it means we are saying 2.9. So this is our clockwise moment. And now we have to find what is anti-clockwise moment. So anti-clockwise moment. We have to find that. And if you see the anti-clockwise moment is due to this Wj, which is the weight of James, and WL. So we again have to see that it should be the perpendicular. So if I just put like this, a small, we have this length as 0.6 and this is our Wj, the James. So actually the perpendicular to this point would be, let me take this distance. So we have to find this distance. Again, it's very easy. So first of all, we would find this. So this is 65 degrees. And if I put this thing as x, so it means cos 65 is x over 0.6 and x would be 0.6 into cos 65. So I keep it like that. So this weight, and we know what is Wj, the James weight. We were given that the weight was, or the mass was 50 kilogram. So 50 times 9.8. I just keep it here and I go back to the question. So mass of the James was 50 kilogram and the ladder had a 12 kilogram. So we have to also find the weight which this ladder is doing because it's also causing a anti-clockwise moment. So we leave this here and now we calculate for, so I just take another color. So this was, what is the W ladder? W ladder would be 12 times 9.8. So I think 9.8 should be written here also. And if I see here again making a diagram, so now this is our W ladder, and angle is again 65, and here this distance that is given in the question, if we go back to the question, it's uniformly distributed, so it is half of 3.2. So half of 3.2, that is 1.6. So it means we have now, so if you want what is this distance, and I would again take another color, and let's say this distance is A because we have taken X. So if you want to know, so cos 65 is A over 1.6, and therefore A is 1.6 into cos 65 degrees. So we would see the anti-clockwise moment now, and we would write them. First of all, Wj, so it would be, let me write again anti-clockwise moment. That is caused due to the James. That would be 50 times 9.8. That is in Newton the weight of James, and multiply by x, and we know x is 0.6 times cos 65. And next is, so this is the moment due to, so I would write moment, and we know it is a anti-clockwise moment. So moment due to James. And now we have to find the moment due to the ladder's weight. And we know the ladder weights we just found, it was 12 times 9.8, and the distance A was 1.6 into cos 65 degrees. So these are the two. This is the moment, and again this is anti-clockwise moment due to ladder's weight. Ladder's weight, and due to James' weight. And this should be because that the ladder is static, it's not moving. So these two weights should be anti-clockwise moment, and the clockwise moment should be equal. Okay, if you calculate this with the calculator, simply taking the values, so I would say I would solve it for you instead of, so 50 times 9.8 times 0.6 times cos 65. That comes out to be 124.24. And the next thing, which is 12 times 9.8 times 1.6 times cos 65. That comes out to be 79.51. So if you add both of them together, 124.24 with this, so it comes out to be 203.75 Newton. And because clockwise and anti-clockwise moments should be equal, so we would say F wall. Let me take another color so that it's more clear. So let me take, so F wall times 2.9 is 203.75 Newton. Okay, so it means F wall would be 203.75 divided by 2.9. So if we divide 203.75 by 2.9, we get 70.3, 70.26, but let's round it off to one digit. So it becomes 70.3 Newton. So that's the reaction which we see here. So that is F wall. So F wall is 70.3 Newton. So that gives us the answer of our first part, which is the reaction force the wall applies to the ladder. We would do now the second part, calculate the reaction force the floor applies to the ladder. And I should say there are two ways of doing it. One way is that we apply the linear equilibrium, that is sigma fx and sigma fy is equal to 0, and find. And second is we apply again the rotational equilibrium, and now instead of making the pivot at the base of the ladder, we would make it at the top of the ladder. I would do it with the both ways so that you understand. One important thing to understand is that now the floor is not a frictionless. So it means if the floor is not frictionless, it's not only a vertical component, and we would do it in the next part. So now let's come to the second part where we have to find what is the reaction force of the floor applies to the ladder. So let's go back to our diagram and look at our floor. So this is our floor, and as we know, this is non-frictionless. So I would say there is a reaction force which is opposite here. So this one is a reaction force from the floor. So I would say, let's say Fr, which is a reaction force. So let's make it otherwise. So let's say reaction force from floor. And it has also a horizontal one because we see that the a reaction from the wall is, which we just calculated, which is 203.75 divided by 70.3 Newton. So there has to be, so if we see there is a, I would just draw it. So this is our reaction from the floor, which is vertical, and this is our horizontal, which has to be equal to 70.3 Newton. Why? Because translation equilibrium wants that whatsoever is in the x direction, they should be equal so that sigma fx is equal to 0. So RF. So we would do it both ways. So let's, yeah, we can do it here. So what we have, sigma fx is equal to 0, and therefore, so reaction, and if I say 70.3, which is on the right, in the right direction, and we say there is an opposite because it has to minus reaction of force in x direction. I am writing fx, so it means I am saying this thing. I just take another color. So I am saying this thing is rfx and this may be rfy. So it means our, this is our, and now we have to see what is sigma fy. That is should be 0. We have two weights which are coming down. So ladder plus weight of games which are coming up down, they should be equal to what we have in the opposite direction. So I am saying rfy. So if we do like this implies we had calculated WL, so it was 12 times 9.8, which was of ladder, plus James had a 50 kilogram mass, so 9.8. This should be equal to RFY, which is our reaction from the floor, which is vertically up. So we just calculate it quickly. So let me take my calculator and see. So 12 times 9.8, that is 117.6, and then 50 times 9.8, and this is 490. So that is RFY. So if we add both of them together, 117.6, so it comes out to be RFY, which is a reaction in the vertical direction. That comes out to be almost 608 Newton, although it is 607.6. So just rounding off till 1. So this comes out to be 608 Newton. So we have to find what is the force. So I would say we have found this is 608, and this in this direction we just found out to be 70.3. It has to be equal to the reaction force from the frictionless wall. And it so we have to see what is the direction. And so if I make vector, so this is 70.3, this is 608, and this means this would be our resultant force, which I would say RF. And this can be found by Pythagoras theorem. So reaction force is actually 70.3 square plus 608 square. And this comes out to be 612 Newton. And we have also to find its angle. So if, because this is the theta. So naturally theta is tangent inverse 608, that is opposite, and the base is 70.3, and if you take its tangent inverse, it comes out to be 83.4 degrees. So it means you have a flow reaction is actually 612 Newton at an angle of 83.4 degrees. So this we have found out actually by using translation equilibrium, which says sigma fx and sigma fy should be equal to 0. So let's do this question alternate way. Doing this question, we would try to do now this question by rotational equilibrium. So let's do that. Now we would do the same question, the B part, finding the reaction from the floor in alternate form. That is in another way, using the rotational equilibrium. And we know rotational equilibrium is sigma tau is 0. So the clockwise moment should be equal to the anti-clockwise moment. I have again redrawn the forces on the ladder. So if you see, because our floor is not a frictionless, so it has a vertical component and a horizontal component, and we would now find, and this time we would use the pivot this point. So maybe this point, which is I have marked as a B, will be our pivot point. So we will have to do length of the wall. This length of the wall, we had calculated length of the wall earlier. It was 2.9 meter. So I just moved. So yeah, we calculated it earlier. So it was found to be 2.9 meter. And similarly, we can find what is the distance between the wall and the ladder. So the distance between the wall and the ladder would be this angle we knew. It was 65. So I would just say here it was 65. And this we knew it was 25 degrees. So knowing the length of distance between the wall, it would be 3.2, which is the length of the ladder, times cos 65. So I just write it here. You can calculate that. What is that? Okay, so let's have a clockwise rotation first. So I would put it here and say what is our clockwise rotation, clockwise moment maybe. So we are now having a B point as our pivot. So we knew 70.3. So this is 70.3, which was there. And if our clockwise, so we have to see this was opposite. So if I see this 70.3, which is opposite to our reaction of the wall, and with the pivot at B, the horizontal distance is 2.9, and it would cause the rotation in a clockwise direction. So this would be 70.3 times 2.9. So I'm saying actually this force, which is Rfx, so I would just say this is actually our R, reaction of floor in X direction, and 2.9 is the horizontal vertical, because we know the angle should be 90 degrees. Then we see the one from the James. This is also doing a clockwise moment, and also the ladder. So I would just write 50 times 9.8 times. Now from the James, the distance is this one. So we have to find this distance. We knew this whole distance, if you do, is 1.35. So we have to have only this distance. So I would say 1.35 minus 0.6 cos 65 degrees. If you are confused about this, I would just do it quickly here. If you see our small triangle is like this. This is 65. This is our 0.6. And we want to know this distance. This is our question. If you see cos 65, and if I put this as a z, would be z over 0.6, and z would be 0.6 times cos 65. And you have to subtract this because you want to know actually this whole distance. Therefore, I put that. So this, and similarly, the other thing from WL, I just write it here. So it is 12 times 9.8, and in this time 1.35 minus 1.6. Why 1.6? Because in this case, it's the distance where the weight of the ladder is halfway. It's a uniform distributed ladder, so it is in the halfway. So it is times cos 65 degrees. Yeah. So if you see, the clockwise moment would become 203.87 plus 537.25 plus 79.24. So if you add them together, this thing, the clockwise moment comes out to be 820.36 Newton. So this is our clockwise moment, which is caused due to this RFX, due to WJ, WL, which is, and the pivot point is point B. Now we would do this RFY, and we know the 90 degrees distance between the pivot and RFY is actually 1.35. So we would say now anti-clockwise moment, anti-clockwise moment. So if again anti-clockwise moment, this is our pivot and this caused the RFY. So that is RFY times 1.35, because 1.35 is the distance between the point of application of this reaction force and the pivot. And this is perpendicular distance. They both, so both anti-clockwise moment and clockwise moment should be equal. Therefore, we can say RFY times 1.35, it should be equal to 820.36. And this results in RFY is equal to 802.36 divided by 1.35, which comes out to be almost 608 Newton. Actually, it was 607.67 Newton. So we again got this. So we would say this like this. This is 608 Newton, which is vertical. We have uh, other, which is 70.3 Newton. And I just take another color so that it make a little. So if you see, we can do like this. Here, this is 70.3 head to tail rule. This is 608 Newton. And this is our, sorry, so just this is our resultant, which we in the previous we have said RF, reaction from the floor. So this is our RF, and it's the same thing which you see by Pythagoras theorem. RF is equal to 608 square plus 70.3 square, and this comes out to be 612 Newton. And the angle theta, if I see, that is tangent inverse 608 divided by 70.3, it comes out to be 83.4 degrees. So we understand that our reaction from the floor is 612 Newton, and it is at an angle of 83.4 degrees. So what we have done today, we have done a question, an interesting question, which was related to this, where a ladder was leaning against a frictionless wall. The main point was to understand the difference between a frictionless wall and a floor. And then we have solved this question by two mechanisms, or by two ways. One using the, first of all, we applied the pivot at the floor, at the where the wall was touching the floor, and we found out what is the reaction of the wall. Then we, in the first manner, we solved it by translational equilibrium, and we found what are the horizontal and vertical reaction from the floor on the ladder. And we also solved the same question by using the rotational equilibrium. So with this, I end today's lecture. Thank you.